We'd like to take you to a video highlighting another TTT effort, Multidisciplinary Analysis and Optimization, or MDAO.
The next generation of aircraft must be faster, quieter, and have zero emissions. Designing these new aircraft certainly will not be easy, but NASA's building a free optimization framework to help. My name's Justin Gray. I'm a numerical optimization expert, and I lead NASA's open source development project, building a state-of-the-art multidisciplinary optimization toolkit, OpenMDAO. I'm here to tell you why you should adopt OpenMDAO for your design efforts and open the door to tackling the most complex design challenges you can think of. Complex, highly coupled systems are everywhere. Airplanes, air traffic control, custom-tailored materials, battery packs, CubeSats, and wind turbines are just a few real-world examples. Traditionally, engineers have used a divide-and-conquer design approach for large systems. For an airplane, we'd split it up into a wing, a fuselage, and engines. The wing team aims to achieve the most lift, the least drag. The fuselage team works to carry the most people, the lowest weight. And the engine team seeks to create the most thrust, the least fuel. During the design process, each team iterates on its subsystem, and then the final product combines all of the best subsystem designs together. To get better performance, you could add technology or improve the design of any of the subsystems. But today it's getting harder to make ever lighter structures, more fuel-efficient engines, or more aerodynamic wings. And because of these diminishing returns, future performance will come from exploiting synergies between subsystems. You could merge the wing and the fuselage, or embed the propulsion system into the airframe to get better performance. Because of the synergies, the subsystems interact heavily with each other, and this breaks the divide and conquer approach to design. The wing team must know whenever the fuselage team makes even small tweaks, and the propulsion team needs to adjust as soon as aerodynamic changes are made. We're no longer able to design each subsystem independently. Instead, we need design tools and techniques that are as synergistic as the concepts we're designing. We need to tightly couple all the subsystem analyses into a single multidisciplinary model. That sounds great, but it's easier said than done. Models get very expensive when you start tying all that physics together. Especially so if you want to use high-fidelity tools like computational fluid dynamics or finite element analysis. Runtimes skyrocket whenever you bring the high-fidelity analyses into the loop. OpenMDAO was built specifically to tackle these multidisciplinary modeling challenges. To battle higher model costs, OpenMDAO integrates gradient-based optimization techniques with analytic derivatives that are 10 to 10,000 times faster than more commonly used methods. And to support high-fidelity models, OpenMDAO can run directly on distributed memory supercomputers. The high-fidelity MDO research community pioneered these methods, and OpenMDAO now makes it possible for anyone to use them on large, complex systems engineering. The high-fidelity MDO research community pioneered these methods, and OpenMDAO now makes it possible for anyone to use them on large, complex systems engineering problems. We used OpenMDAO to design an advanced propulsion concept called boundary layer ingestion, BLI. An optimized BLI design can produce thrust 10 to 15% more efficiently. To model this, we combined a 3D RAND CFD aerodynamic model and a thermodynamic propulsion model. Using OpenMDAO, we ran this optimization in 20 hours on 400 CPUs. In fact, we didn't just run one optimization, we ran 9 different optimizations at different propulsor sizes. You need large sets of design data like this to analyze the potential of a BLI concept. What makes it possible to do these design studies with multiple optimized geometries? The speed and efficiency of gradient-based optimization with analytic derivatives in OpenMDAO. Here are some other examples. This is an optimization for an electric propeller nacelle for NASA's X-57 that balances the need for minimal drag and maximal heat rejection. And this is a propeller designed with OpenMDAO using a low-fidelity aerodynamic model and a medium-fidelity acoustic model to simultaneously maximize thrust and minimize noise. One of OpenMDAO's most unique and powerful features is that it lets you work with any mixture of low, medium, and high-fidelity analyses in your modeling. OpenMDAO is the most advanced system optimization platform available today. NASA's using it to design faster, quieter, zero-emission aircraft, and we also release it free and open source. There are OpenMDAO users designing wind turbines, electric motors, rockets, F1 race cars, satellites, and eVTOL aircraft. No matter what you're designing, you could be doing it faster and with a lot more physics by using OpenMDAO. So please download it, use it, borrow code from it, or simply take inspiration from it. What could you design if your optimizations ran 10,000 times faster, or you could couple in high-fidelity physics into your system models? To get started, visit openmdao.org.
I would now like to welcome to the stage Justin Gray. Justin leads the MDAO effort in TTT that we just heard about in that video. Justin, welcome to Imagine Aviation.
Hi, Steve.
How you doing today?
Doing great.
Excellent. Thanks for joining us. Justin, if you folks that watch that video, it really sounds exciting. The work you and your team are doing, a ton of possibilities. But let's start off with a curveball right away. What are some of the challenges that people might have in adopting this technology?
Oh, that's a good question. The video paints a rosy picture, and OpenMDAO is really powerful in terms of what it enables you to do. But there are two challenges that I often hear from a lot of industry folks. The first one is that a lot of the power of OpenMDAO comes from its support for analytic derivatives, and there aren't a lot of commercially available tools that provide derivatives. So sometimes you don't have the tools you need to take advantage of the power. And the second one is that, it's a new modeling paradigm, and it's sometimes hard for people to develop and model in a new paradigm. So I think that the gains that you get from using OpenMDAO are worth it. And we're actually working really hard in T-Cube to produce more foundational tools that have derivatives. One of the best things about OpenMDAO is that it can allow you to develop a next generation of your tool, provides that computational layer so you can build tools with derivatives. And we built, as you saw, cycle models with derivatives, jet engine models. We're working on aircraft design tools. And a lot of the high fidelity tools from the previous talk that you saw with Mujib, those all now have derivatives too. So hopefully in just a few more years, we'll sort of reach critical mass and there'll be enough derivatives to go around for everybody.
Yeah, and like any new development, MDAO has a set of challenging questions from your potential users. You've heard them all. I mean, even myself from just the outside, you'll see and hear that maybe people say optimization in general, it doesn't work, or we've tried it before. It really doesn't give us exactly what we're looking for. How do you respond to pushbacks like that? How can OpenMDAO actually make things better or make things worse if they're done incorrectly?
That is the classic response when I tell somebody that I'm an optimization expert. I often hear, "Oh, optimizers don't work," and I think it's actually a really fair criticism because oftentimes, at least historically, they didn't work. I think there are two reasons for that. The first one is that without analytic derivatives, it's actually really hard to get a very tightly converged, stable optimization running. And so the type of convergent analysis people are used to getting from their solvers, they don't get that from an optimizer, and that's very frustrating. However, analytic derivatives really does fix a lot of those issues. I would say that analytic derivatives themselves fix one of the big numerical and computational challenges that have plagued optimization. The second one I think is a little bit more subtle. You actually do need to know what you're doing when you set up an optimization. It's not as easy as people think simple optimizations are. If you just want to maximize lift, with a minimized drag, something like that. But when you start applying it to real problems, you often forget about a certain constraint. And every time you run the optimizer, there's an old joke that says the definition of an optimizer is a computer program that automatically finds every bug in your program and every weakness in your model. And so often what people find is when they run optimizations, all those weaknesses get exposed and they add more and more constraints. And then by the time they're done adding all those constraints, they think, well, I could have gotten that answer anyway. I didn't need the optimizer to tell me that. And that's often true, except as problems get more and more complex, we don't know what the answer is ahead of time. And so you still go through that process of adding more and more constraints. It's just that you didn't know what the answer was. And there again, I think OpenMDAO helps because it's so much more efficient that you can afford to do 3, 4, 5, 6, 7, 10, 20 rounds of optimization. In fact, you can even afford to do entire design sweeps where you, the engineer, vary one of your key design parameters over a certain range and optimize as you go. And derivatives really enable that. So I would say that the computational performance and the computational stability of derivatives really do change how optimization can be used at an organizational level.
Right, right. And there's a question in the IO it's related to this, but it is mentioning or asking for what is the ROI of a single multidisciplinary model, the cost of computation and modeling, compared to the expected performance gain?
I think it depends heavily on the problem you're solving. If you are designing a tube with wing aircraft, then building a fully coupled aeropropulsive model, for example, where you tightly couple the propulsion system and the airframe and you build it all, the return on investment is very low there. I mean, in a sense, that's by design. We design a tube with wings specifically to decouple those systems. However, if you look at a boundary layer ingestion system like that tail cone thruster idea that we had there, I would argue that you cannot properly design that system without that coupled model. So in a sense, the ROI is infinite because you can't design the aircraft without it. Even at the conceptual level, we've found that that's fundamentally true, that you just simply do not have the right answer without the fully coupled model. And in that case, specifically boundary layer ingestion, you're reliant on 3D RAN CFD at a minimum for your aerodynamics. And so at that point, the computational cost is so high without derivatives that it's not even possible to do it. So I think there's a spectrum. If you go all the way back to like traditional aircraft, you could argue that a fully coupled multidisciplinary model with derivatives maybe doesn't buy its way into your process. If you're looking at boundary layer ingestion or highly flexible aircraft or something where there's a strong thermal coupling, for example, on a high-speed aircraft, I think that the return on investment is very high in terms of reducing risk and sometimes just making it possible to achieve that design at all.
Well, it makes me think as well is we talk about the optimization issues and benefits for today's aircraft, single tube and wing. But I got to assume that there's a lot of differences between what we talk today, what we're envisioning in the future. So what's so different about today's aircraft challenges that traditional design methods, or tomorrow's aircraft challenges either, that traditional design methods won't really work as well as they should?
I think the answer depends a lot on your flight regime, but in all the flight regimes that are sort of highly relevant, I think highly coupled models will be important. So if we talk about traditional commercial transport, traditionally a tube with wing aircraft was decoupled enough, like the previous question implied, that you didn't need this tightly coupled model. But as we start to go to hybrid electric aircraft, the interplay between fuel weight and battery and how big should your jet engine be versus how big your electric motor should be, it turns out that's really hard to answer without a fully coupled model. So I think that's a situation. And if you start looking at any kind of advanced configurations like a hybrid wing body or boundary layer ingestion, things where there's two systems interacting more strongly, I think you have to consider it. And the reason we're going in that direction fundamentally is that we've reached a point of diminishing returns on any of the subsystems. So we can make jet engines a little bit better, but we can get a much better gain in performance by coupling the propulsion system and the airframe, so that the gains there are higher. If you're talking about eVTOL aircraft, those aircraft are so sensitive to empty weight that every little decision you make could end up meaning you have one more or one less passenger on board. And that could make the difference between a viable aircraft and a non-viable aircraft from a commercial perspective. And when you're balanced so tightly on a knife's edge, optimization really helps a lot there. And for something like a supersonic airplane, never before have they had to build an efficient supersonic airplane that was also quiet. And those two things are competing, heavily competing. And when they compete, they interact. The quieter you make it, sometimes the less efficient it is. Or you have to find some way to get both at the same time. And those kinds of situations require optimization because you're navigating huge geometric design spaces. Little tweaks in the structure can affect the geometry, can affect the noise and the performance. It's just too much for the human mind to set up. So you need these models that can give you reliable, close converged answers so that you can then look at trades over an optimized design space.
I mean, you're talking a lot about a significant amount of paradigm shifts. We've heard a lot of that the last couple of days. This is absolutely no different. And anytime when you talk about paradigm shifts or the introduction of new technologies, and maybe what can help have the private sector or even others embrace that. Sometimes it's training in a new tool. Talk to me about the need for good optimization training and why it's useful for design work.
It's actually a pretty strong need. It's a little funny. Sometimes I say that OpenMDAO has created an arms race between the OpenMDAO developers and its users. And by that I mean that the tool has made it so possible to build really complex optimizations, and then the users quickly run off and build an optimization that's far more complex than they realized, and then the optimizer doesn't work. That's the classic, the optimization didn't work for me. And often it's because they posed the problem improperly. And that's not because they're not talented engineers, they are. It's because they didn't realize that there was this weird optimization detail that they had to account for. There are some universities that do a good job teaching graduate level optimization courses. The optimization problem formulation isn't really taught at the undergraduate level. And even once you graduate, if say you come into NASA in my branch, we don't even have a rigorous formal optimization training curriculum yet. There are some really great classes. The IAA offers a 2-day class that I think Professor Keem Martins from University of Michigan teaches every once in a while. But yeah, I think in part because the types of optimizations that we've been able to build traditionally have been simpler, the need for understanding complex optimization hasn't been there. But now that OpenMDAO is here and lets you build these massively complex optimizations with thousands of variables and hundreds of constraints, with many disciplines interacting, having some optimization expertise on your team, somebody who can look at that problem and tell you why the optimization didn't work, is sort of a critical need. I would say that having an optimization expert is another discipline or another expertise you would consider in your systems analysis group. We're used to having propulsion systems analysts and aerodynamics and airframe systems analysts, but I would argue that you also need somebody who's very skilled in optimization itself.
Yeah, it makes a lot of sense in that. And Justin, this is really a refreshing conversation. You're very honest about the bumpy path it can take to get to current valuable version of OpenMDAO. It's a question in the IO that asks, on that note, what have been some of the learnings and successes and failures that you've managed along the way in this journey?
Now, somebody in the conference IO may have heard one of my previous talks. At Aviation, I think this year, I gave a talk titled "How to Succeed at MDO by Failing All the Time," and I chronicled the 14-year history of OpenMDAO and the 3 major epic failures that we had. I think it's a real credit to NASA that OpenMDAO survived those failures, that it's an environment that encourages and celebrates that kind of work. I'm not going to claim it was easy, but we've rewritten that framework from scratch 3 times. Our original implementation could not scale to supercomputer-like levels, which you need to do if you want to support CFD or finite elements. So, and in fact, our original implementation didn't even support derivatives properly. So we made a big change and we rewrote the whole framework to support distributed computing and high fidelity work. And then when we did that, we found out that it worked great for that, but it didn't work for low order and single processors type stuff anymore. So we had just traded one problem for another. So then we went back and we refactored everything and started from scratch all over again and tried to bring some of what worked in the original version for single processor stuff and some of what worked for the high fidelity stuff, and we merged them together. And that's really what made OpenMDAO 3.0. I would say that we have failed far more often than we've ever succeeded. Only in the last 2 or 3 years, really since like late 2017, early 2018, do I think OpenMDAO has really had the capability to design new aircraft to handle these big coupled problems in a way that would be ready for a non-researcher, non-developer. And that's, I think, a credit to NASA, and it shows how hard some of these topics are. I mean, if it was easy, everybody would do it. But yeah, it's been a really long road. Like I said, we've rewritten it from scratch several times. And each one of those rewrites is really hard on our user community. I won't even pretend that I handled that situation particularly well. I think I learned a lot as a software developer about how to manage, epochs of code. But I would say that that's probably the biggest lesson I learned, which is that your code base is not sacred, and you need to be honest with yourself when things aren't working, and you need to be willing to throw it out and start over again. And just hopefully your development process is such that the start overs, each successive restart is faster than the last one. And if you can innovate fast enough to get in front of your failures, you'll survive.
Yeah, and that's again very refreshing to hear. It sounds like the work of you and your team, they really are, you really are embodying the words that Catherine Jabakloff said on day one, that yesterday, that Simon Sinek said yesterday, about embracing the learning, embracing the failure, understanding you can't always be successful, and that's fine as long as you learn from it, persevere, and drive for advancement. Do you see that fortitude in your team and the people you work with, or where is the struggle sometimes with continuing to having to adjust?
Well, I remember the very first time that I realized we had to start over. I was working with a student at the time, and we had been arguing for 3 days, and he'd been saying, like, basically what you have will never work, and I didn't understand. And then finally, I don't remember what he wrote, but he wrote something on the whiteboard, and I got it. I had this epiphany moment, and I must have gone like completely white, because I sat down in my chair and I mumbled to myself, oh, we're going to have to start all over. And the student got really scared. He thought I was like upset and angry at him, but I wasn't. And then what followed was like 6 months of me begging and negotiating with the rest of the development team to convince them that we had to restart. Nobody wanted to do it. Everybody felt like that was the wrong move. But in the end, I sort of asked, I said, like, let's just take 6 months. If it doesn't work in 6 months, we'll go back to the old code base. And that was the deal we made. And it turned out we were able to get something that proved we were on the right track in 4 months. After that, it was easier because the team sort of learned that we needed to restart. Although I will admit that I sort of learned the wrong lesson there, because the second restart that we did, when we had to re-go from parallel to supporting parallel and serial, I feel like that rewrite was actually unnecessary. Not that it was an epic failure to rewrite it like that, but I think we could have gotten to where we are today without restarting. But the first rewrite had gone so well that I thought, well, what could go wrong? And so I think the team has learned to accept that, and we all sort of recognize that when you run into those roadblocks, that's the moment where you know you're onto something good. And if you can figure out how to get past it, there's this vision to where you'll be in 6 months or a year that makes it worth the risk. You do have to have an organization that can support that, but I think NASA is a good place for that.
Oh, that's great. And yeah, and the perseverance, as you say, it helps to have that organizational support. When you flip over to the other end, the private sector, that has different constraints, different pressures, that maybe don't like to hear the perseverance story that you're talking about. They like when we do it, but on the outside, it's fair. It's fair from their perspective. So there's a question in the IO tool that's related: is what would you say to engine manufacturers who really resist trying to design a different engine for every aircraft?
Well, I don't work for an engine manufacturer, so I won't pretend to know all the challenges that they have there. But I will say that if you're having trouble designing engines fast enough, then you should look carefully at where those bottlenecks are. If you really don't believe that you need a different engine for every aircraft and that the airframers are being unreasonable, that's one thing. But if we take as a given that really it would be better to have a different engine for every aircraft, then my advice would be to go after every and any bottleneck you can find in the order of importance that would prevent you from doing that, whether that's computational or manufacturing. And maybe there's an answer there. Maybe OpenMDAO and the design folks need to bring manufacturing more into their process. But I think if you look at companies, some of the more innovative companies out there, what they focus on is being able to churn out products at a faster cycle. And I guess, again, I hesitate to tell engine companies how to do their job.
Right.
But let me just turn that around and say, if there's a place in your design cycle that you feel like there's a bottleneck, that maybe it sounds like some of what you heard today from OpenMDAO can help, reach out. Let's talk about it, and maybe some of NASA's technology could pave the way to clearing that bottleneck and make it possible for you to design engines more quickly.
Yeah, because you're releasing more open source as you develop, right, for the marketplace.
That's right. We're pretty unique. We actually release our software even before it's finished. Almost everything we do is developed open source in the public eye. We just recently released a package built on top of OpenMDAO called MFIS, which is sort of a library that helps you tie in all your high fidelity solvers into OpenMDAO and tries to standardize and make approachable some of the really great work that comes from academia. And it's a big collaboration between government and some industry folks in academia. So please check out the MPhys library, github.com/OpenMDAO/MPhys, MPHYS.
That's great. That's a perfect place to segue. Justin, thank you so much. We really appreciate your Q&A. We appreciate the video and explanations regarding your work on MDAO. Thank you for joining us today.
Thanks, Steve. It was my pleasure.
Great. Next, I want to welcome to the stage